Alright everybody, you made it. This is the last one, 11.3. So what we're going to do is we're going to test and estimate a single variance of deviation. Variance, remember, is your sigma squared or s squared. So if you look at your formula sheet, which you're really going to need your formula sheet and your chi-squared table to really understand what's going on. Okay, so this is another way to estimate. We're testing a variance, so that's what you're going to look for in the problem. Okay, and on your formula sheet, you're going to find this as the third one down, I believe. Actually, it's going to end up being the fourth one down. It's actually below the confidence interval. I'm going to do the confidence interval last because it's the hardest. Okay, so here's the formula that you need. This is pretty straightforward because in your problem, you're going to know what n is. You're going to know the sample standard deviation and the population standard deviation and or variance. I guess I probably should remind you, S is standard deviation. We should know that by now. Okay, and then s squared is your variance. Now your problems might give you one or the other, so if they actually give you standard deviation, you must square it. If they actually give you the variance, that's the number that you use. Okay, degrees of freedom in this problem is your n minus 1. Alright, before I actually get to the problem, working with these distributions, it gets a little bit tricky because now they might say left tail, they might say right tail. You just kind of got to be careful. So what I want you to do is grab your chi-squared table just so we have a little bit of a visual. If I say find the chi-squared, the actual number, so that the area to the right, which is normal for a chi-squared, so it's actually the number that we want, of chi-squared is at the 5% level. Okay, now how do you do that? Well, on your top, degrees of freedom is on the left. The top is your right tail area. I want 5% to the right, so that's as normal. So if you go down to degrees of freedom 10 and go over to the part on the top that's 0.050 is actually how they have it, and 10 over here, see where they meet, you're going to notice you get 18.31. So if they say to the right, that is the normal. That's what we want for a chi-squared distribution. So it's straightforward. You do not have to use any tricky stuff. What's tricky is part B. They say find the chi-squared so that the area to the left of chi-squared is the same amount. Well, this table doesn't give me any areas to the left. So what number on top do I look for? Well, if you kind of look at this picture, if I want 0.05 to the left, that means I want 0.95. I know it's small and you can't really see it very well, but 0.95 to the right. So what you need to do is go to 0.95 on the top, still your area degrees of freedom 10, and you're going to notice that you find the 3.94. Because how this chi-squared works, it starts from 0 on this side and goes over to that amount. So 3.94 is relatively close to the left side. And that's the chi-squared that gives you that amount. So you're going to see a variety of things, and that's how the table is being used. So like I just said, I just talked about how to use these two. If I'm looking to the right, straightforward. If it's left, you're going to have to do 1 minus the p-value, or what we're looking for. So in like the last problem, it was 0.05, so we get 0.95 here. And that's how you use the table. The two-tailed thing is a little bit trickier. You're going to have to... and I'm going to do an exact problem using this, so I'm not really going to talk about it too much, but remember you're going to have to split it in half and then multiply by 2, and we'll talk about that. So here's one of two straight out examples I'm going to show you. The first one is testing, okay, the variance. So they're going to give you this type of scenario. Suppose the variable of interest, weight loss after a 6-month diet. Notice they give you standard deviation, 5.7. Okay, so that is your sigma. That's known to be happening throughout time, or however you want to look at it. The new modification, the new diet that's implemented, took a sample of 21 people, and they have a new standard deviation of 4.1. So now at the 1% level, does this indicate the sample variance has changed? So that's what you're going to test. So here's what you got to think about. I talked about that they gave you sigma and S, but we are actually testing variance. So be careful if that happens. They're going to switch it up on you. They're going to give you some of everything. So since sigma is 5.7, okay, you'd have to square that. 5.7 squared gives you the 32.49. That's what you have to give me in your null and alternate hypothesis. We are testing a variance, so it has to be the squared one. Okay, so not the 5.7. Some of you are going to end up writing that on the test, I have a feeling, so please don't do that. Use the squared. It's variance, so it has to be the squared one. Always, 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 the null hypothesis will be the variance is equal to whatever they claimed before. So that'll always be your null. In each problem, obviously, the number will change, but that'll always be your null. And then the alternate is going to be kind of what they state. It'll be still variance. It'll still be the same number, and then it'll be either left tail, right tail, or two tail. Okay? So that's how that works. Now you need to find a chi-squared. Chi-squared number. This is really easy once you have these numbers. Okay? So n is 21, so it ends up being 20 in here. I need a pen. And then times this s you got before. This was 4.1 on the previous slide. They got that in their sample. And then we know that this is always going to be your null. And then you end up getting a chi-squared number of 10.35. Okay? Degrees of freedom is n minus 1 in this section. So you know that degrees of freedom 20. So if you go to degrees of freedom 20, figure out where this number falls between. And that's what you want to look for. So here's what gets tricky. Okay? If you go and figure out what two numbers this 10.35 falls between, look what happens on the top. Okay, they're giving you 0.975 and 0.95. I have no idea what's going on with that because that is way too big. And some people are like, ooh, this is no good. But be careful. Alright? This is a two-tailed test. So they might give you one tail or the other depending upon where you are ending up on your graph. Okay? So it just so happens that we're towards the left side of this particular graph when our degrees of freedom is so high. This curve gets spread out a lot more. Okay, you might end up being 50s and 100s over here, so we're actually on the left side of your curve. So how do I kind of figure this out? If you're on the left side of your graph, and this is going to be, if you look at the top, it's your top kind of goes 0.995, 0.990, 0.975. Any of the 90% situations, that's signifying that you're on the left side of your graph. If you're on the right side where you get the 0.1, the 0.05, the 0.025, then you're on the right side and you just write it down as it is. But if you get the 90%, you will always have to subtract them from 1. Okay? Because the chi-squared is saying everything to the right. So our actual p-values are going to be 1 minus that. Okay? So that's hopefully that sort of kind of makes sense. Now this is going to be the interval when you subtract it from 1, about 2.5% to 5%, all right, for the one tail alone. Now this was a two-tailed test. So that's where it kind of gets tricky. You're like, okay, I got to subtract from 1, and then you end up having to multiply this thing by 2 to get the two-tailed part. Okay, and then this is kind of how you finish this off. Since the p-value is greater than 1, because obviously it's going to be 5% to 10%, so it's greater than the 1%. We do not reject the null hypothesis. We fail to reject. So what did we do? We conclude that the population variance has not changed. Okay? There's not enough evidence to suggest, and I forgot to write this in here, so at the 1% level, okay, there's not enough evidence to suggest that your variance has changed. And you can go in depth like this. You can be, as long as you say the percentage level, and then we fail to reject, and we conclude that the population variance has not changed from the 32.49. There's not enough evidence to suggest that. Okay, so in this problem, just a little recap. Two-tailed test. Okay, you get your chi-squared number. You go to your table, and if you get the bigger percentages, you're going to have to subtract them from 1, and this is the answer you would get if it was a one-tailed. Actually, what I should do is say this is the left tail idea if I only was looking at the left tail. Okay? But I must multiply by 2 to get the two-tailed test. Alright? So we found this originally, and then we had to multiply to get the right tail. And that's just kind of how it worked out. So you might get one or the other, and that's where this gets a little bit tricky. And then basically, once you get your p-value, you answer the question like any other one we've done all year. Okay? That's the test. So there's an example for your test. The other thing we're going to do is a confidence interval. And you're going to see confidence intervals not only for the variance, but also for the standard deviation. Here's the kicker. How do you go from variance to standard deviation? It's just the square root. Okay? So here's my encouragement to you all. If you look at your formula sheet, I believe they give you the variance one, and this is the only one that they actually show you on the formula sheet. Now, I might ask you to do a confidence interval for the standard deviation. Okay? You do it for variance, get the answer, and then just take the square root. Okay? And that's not all that bad. This isn't overly tricky except for these upper and lower chi-squared bounds. That's where it gets tricky. If you grasp that part, this is really, really easy. So I'm just going to jump to an actual example, okay? And then we will kind of see where we go from there. All right? Now these confidence intervals, it's not that you add and subtract the error anymore. Okay, remember with confidence intervals, we always had like y hat minus the error, and then y hat plus the error. Well, there's no magical error formula. What we're going to do instead is get these lower and upper bounds to try help us out. Okay, so we're going to know exactly where the endpoints of the interval are going to be strictly by our standard deviation and our variance. Okay, with all the stuff combined. So here is an example. So I want to find a confidence interval for the variance. So I actually specify variance in this problem. We have a random sample of 30, a standard deviation of 3.4. Okay, and I want a 95% confidence interval. Alright, so I kind of list all these things out. You're going to need to know all of that stuff. And what I'm going to do is jump to this problem. Now, I actually have all the answers here, but I don't know how these things magically showed up. Okay, that's what we need to try work on. So here's what I'm going to try and kind of show you. Chi-squared curve is not necessarily symmetrical. Okay, I need a 95%. Okay, 95% confidence interval. What does that mean? 95% needs to be in between the interval that I pick up. So what we need to think about is what is left over. Hopefully you're like, oh, there's 5% left over. Okay, and now remember, in between means that there's some in the left tail and some in the right tail. Hopefully all of you are thinking right now, duh, Mr. Wilson, it's 2.5% or 0.025 in each tail. Hopefully you're like, yeah, that makes complete sense to me because that adds up to the entire curve, but I still have no idea where you magically got these stupid numbers from. Okay? Well, if you go to your chi-squared table, this means chi-squared upper bound is what that means. Alright, that's all they kind of signify it as, and this is basically what this is going to be is the bigger number that you find. Okay? Well, how do I find the upper bound? Now, what you should do is, means it's the right one. So chi-squared upper. Chi-squared tables give you information that's to the right. So I need to find this exact number. Alright, so what chi-squared number gives me a p-value of 0.025 to the right at the degrees of freedom of, in this problem, 29. And that's what I showed you on the previous page. Okay, so go to your chi-squared table, degrees of freedom 29, and since it's to the right, I actually look for, in this upper bound one, 0.025 on the top, 29 on the degrees of freedom. Where do they meet up? Okay, and you should find out that those two meet up at the 45.72. So on this curve, where if this would be a number line, this would be 45.72 units over. And that would give you that only 2.5% are still to the right or in the right tail or the upper bound. Okay? So that's where the 45.72 comes from. That's the right tail. Well, what number is the line so that 2.5% are to the left? These things are not symmetrical, so it doesn't work that way. So what we need to do now is think about how does the chi-squared table work. This is the hardest one of them all. This is the magic line. What percent is to the right? Well, 95, the entire interval, and the 2.5% together. So it's actually 0.7975. Okay, and that's actually a heading on a column. So this one is going to have the 0.97529. Where do they meet? And they also should meet at this magic number right here. Okay, so it's all about the lower bound is the left tail. And what magic number gives me that? Well, the chi-squared table, your table in your hand, the brown chart, is only thinking about information to the right. So if I want 0.025 to the left, it's 0.975 to the right. And that's the heading I look at, degrees of freedom 29. That's where that number comes from. Okay, now some of you are wondering, well, why do we put the upper one on the left side and the lower one on the right side? Well, this is a confidence interval, everybody. Okay, notice the numerators are exactly the same. And in an interval, I want the smaller number on the left side, so I have to divide by the bigger number. Okay, and on the right side, I want to divide by the smaller number. That's the idea. Okay, and n is 30. Your s is 3.4. You have to square it. Don't get that mixed up. They gave you the standard deviation. So your interval will end up being that if you do your math. All right. And then how do you figure it out? Thus, we're 95% confidence that the interval from 7.3 to 20.89 contains the population variance. Okay? Now, that is if I asked you to find a confidence interval for variance. Now, I might be a little bit tricky and say, hey, what if I just want you to find a confidence interval for standard deviation? Instead of sigma squared, maybe I just write sigma. If I do that, this page, identical. What you do at the end is you just take the square root. So you just take the square root of your answer. That's all you do. Okay, you take the square root of this, that, and that'll end up getting you your standard deviation interval. And it'll be the exact same sentence, you just take the square root. So you just got to be prepared to and make sure you read closely. Alright, this will be your last assignment for Chapter 11. And Thursday and Friday, or the next 2 days this week, we'll review and then test. So hopefully you all have a wonderful evening, and we'll see you later.